starting, we will learn a new part of the linear algebra, matrix decomposition. In this part, we will get to know the eigenvalues, eigenvectors, and singular value decomposition. Before we come to the subject, let me introduce a concept, linear independence. A set of vectors is linearly independent if any elements of the set cannot be expressed as a linear combination of the vectors. For example, the vector S. The condition for linear independence is to seek a set of non-zero scalars 4, 3, 2, and the vectors can be regarded as a linear combination of some basic vectors, like here 1, 0, 0, 0, 1, 0, 0, 0, 1. The last S is the one which the columns are not linearly independent, since we can't use the basic vectors to represent it. Combined with what we learned on the last page, the rank of the matrix is the maximal number of linearly independent columns or linearly independent rows in the matrix. For example, the matrix S has 2 non-zero rows. That is, matrix S has 2 independent row vectors. So we can see the rank of S is 2. After going through the prerequisite knowledge, we come to see one of the most useful and practical concepts, eigenvectors and eigenvalue. Recall what we have learned, linear transformation, eigenvector and eigenvalue can give us the information on scaling and rotational characteristic of a matrix. That is, eigenvector represents rotational characteristics and eigenvalue represents the scaling characteristics of the matrix. Start with the mathematical definition. A alpha equals to lambda alpha, where A is the matrix and alpha is the eigenvector of a matrix A and lambda is the eigenvalue of matrix A. As shown in the animation, we can understand the concept of the eigenvector in a more intuitive way. Assume we have the matrix A, we can use the orange line to show the different vector U, and the vector U is transferred to its corresponding vector AU in the blue arrow line. So, compared with the original vector U and the transformed vector AU to check which one changed both its direction and magnitude and which one changed its magnitude only. From the animation, there are several times when the vector U and AU are in the one line. In other words, only when the vector U changes magnitude, not the direction, and it is transformed by A, can we say this is the eigenvector of the matrix A. Now we know the eigenvector changes only its magnitude when applied by the corresponding matrix. Then the question is how much in magnitude it changes, exactly how much. The indicator showing the magnitude change is called the eigenvalue. For example, if the eigenvalue is 1.5, it means the magnitude of the vector AU gets larger than the original magnitude by 50%. Therefore, the matrix A multiplied to its eigenvector alpha is the same as the eigenvalue multiplied to its eigenvector. And also, there is another way to understand the meaning of the eigenvector and eigenvalue directly from the equation. Let's look at the right side of the equation, which is the scalar lambda times alpha. Recall what we have learned from the linear transformation. It is only scaling the vector, and the angle of the vector doesn't change. In other words, this part can scale the vector but doesn't do any rotations to the vector. Let's look at the left side of the equation A times alpha, which is the vector times a metric A. Actually, when we multiply a metric to a vector, the vector will scale and rotate in some degree at the same time. But there can be special vectors that only scales and doesn't do any rotation by the matrix. These special vectors are called the eigenvector of the matrix. There are several ways to define the eigenvalues and the eigenvectors. When rewritten, the equations A minus lambda I all times alpha equals 0. When the equations has a non-zero solutions, alpha if and only if the determinant of the matrix A minus lambda I equals 0. Thus, the eigenvalues of A and the values of lambda that satisfy the equation, the determinant A minus lambda I equals 0, where I is the n by n identity matrix and 0 is the zero factor. Finally, when we set the characteristic equation of matrix A to 0, then we can compute the lambda roots. The eigenvectors corresponding to each eigenvalue can be found by solving the components of alpha in the equation A minus lambda I all times alpha equals 0. We have an example to find the eigenvalues and eigenvectors of matrix A. In such problems, we shall find the eigenvalues of the matrix. To do this, we find the values of lambda which satisfy the characteristic equation of matrix A, namely those values for which the determinant A minus lambda I equals 0, where I is a 2 by 2 identity matrix, so we can get 2 lambda roots, 2 and 4. Once the eigenvalues of matrix A have been found, we can find the eigenvectors associated. Taking lambda as 2, according to the formula A minus lambda I times alpha equals 0. We can get the x1 equals to x2. Therefore, we can get the corresponding eigenvector is 1, 1. Same way to get another eigenvector minus 1, 1, when lambda equals 4. Eigenvectors and eigenvalues are numbers and factors associated with square matrices, and together they provide the eigendecomposition of a matrix that analyzes the structure of this matrix. Eigendecomposition decomposes a matrix A into a multiplication of a matrix eigenvectors U and a diagonal matrix of the eigenvalues sigma and UT. Usually, we also put together the set of the eigenvectors of A in a matrix denoted U. Each column of U is an eigenvector of A. The eigenvalues are stored in a diagonal matrix denoted the sigma, where the diagonal elements given the eigenvalues and all other values are zeros. We can rewrite the equation as A equals U times sigma times UT, where U times UT equals I. These are normalized eigenvectors. If they are not normalized, then U times UT is a diagonal matrix. The eigen decomposition of matrices is practical. The principal component analysis is obtained from the eigen decomposition. Given a data matrix A, the principal components of A are the eigenvectors of ATA. Principal components analysis PCA for A is to find the eigenvectors and eigenvalues of the matrix ATA. Principal component analysis PCA can help us with dimension reduction, optimization problems, regularization for preventing the overfitting problem. After we know about eigenvalues, eigenvectors, and eigen decomposition, we enter into a related part, singular value decomposition, SVD. Singular value decomposition takes a rectangular matrix defined as A, where A is an m by m matrix in which the n rows represent one object and n columns represent the attributes of the object. The SVD theorem states U times sigma times Vt, where the columns of U are the left singular vectors. Sigma, the same dimensions as A, has singular values and is a diagonal matrix. Note that sigma is not necessarily a square matrix. The singular values are arranged in descending order, and the columns of V are the left singular vectors. The SVD represents an expansion of the original data in a corresponding system where the covariance matrix is diagonal. Calculating the SVD consists of finding the eigenvalues and eigenvectors, of ATA and AAT. The eigenvectors of ATA makes up the columns of V. The eigenvectors of A times AT makes up the columns of U. Also, the singular values in sigma are square roots of eigenvalues from ATA or AAT. Here, we geometrically show SVD. The SVD can find an orthogonal basis in space and map this orthogonal basis to the image space through the matrix multiplication. The singular value sigma is the corresponding strange vector. From this figure, we can see the original matrix A can be factorized to the effects of the rotation, scaling, and projection by SVD in each step. And the final result is shown in this corner. Before getting into the example, we first interpret U, sigma, Vt related to the data. U maps the n points to an n-dimensional concept space. So What is the concept space? Actually, row vectors and column vectors of matrix A can be transformed into lower dimensional space. This space is called the concept. In other words, row vectors and column vectors can be mapped to a concept space, which has smaller dimensions than row and column vectors of matrix A. Sigma diagonal elements can be interpreted as the strengths of the concepts in the concept space, like how much can data be summarized by the first concept and so forth. VT maps concepts back to the features, like which features adhere to each concept the most. The first example is users renting movies. There are two types of movies in concept: sci-fi and romance. Recall the SVD formula. A equals U times sigma times VT. And here, U is the user to concept similarity metric. V indicates movie to concept similarity metric. Sigma is its diagonal element strength of each concept. And the first metric is U. The first column of U means the sci-fi concept. And the second column of U is romance concept. Now, as you can see, the U metric maps users to the concept space. The first four users like the sci-fi concept. On the contrary, VT maps movies to concept, highlighting that the first three movies have a strong sci-fi component, whereas the last two tend to romance. What about the third columns in U and third rows in VT? Actually, it is noise, since the third diagonal element in sigma is 1.3, much smaller than the other two, 12.4 and 9.5. So, compared with other two, 1.3 telling us that the strength of the component is very low. Another example is using SVD to compress the image. We treat the image as metric, and the SVD is applied to keep the most feature. As shown in the figure, the higher K, the better quality the image has, but also the more data needed to be encoded. We now choose a number K equals to 70 of singular values that we are going to use for the approximation. We now take only the first 70 columns of U and V. As for sigma, it contains the 70 largest and the most important singular values. From those two formulas, we can see the total pixel numbers getting smaller. This is how we compress the image by SVD. That's the end of linear algebra part. Thank you.